Hello, how you doing? Have you heard the term RAG and you're not quite sure you know exactly what this is or how it works? Well, if so, then watch along with me for the next few minutes and I'll quickly get you up to speed. Okay, let's get started. Before I talk about RAG, let me first talk about embeddings. RAG depends on embeddings. So I want to quickly make sure you understand this important concept. Embeddings are vector representations of data. In our case, text data, but it could be any data such as images, audio, or video. There are specialized LLMs, also known as embedding LLMs, that can take in data and generate embeddings. In this example, I am showing an embedding LLM generating an embedding for a text document. Again, an embedding is just a sequence of n-dimensional vectors. Quick note, I have a video that deep dives into embeddings. Feel free to check this video out if you want to go a bit more into this topic. But for now, I'm going to keep going. So now with the definition of embeddings in place, why does RAG depend on embeddings? Well, this is because embeddings, when stored in a vector database, enable RAG systems to efficiently retrieve contextually relevant documents, which are then paired up with prompts to the LLM, dramatically improving the quality of the LLM response. The first step in building a RAG system is getting your proprietary data into a vector database for easy, quick retrieval. First, you take your proprietary text documents and systematically create embeddings for each of them. Once you create these embeddings, you insert them into a vector database. Okay, so now with all your embeddings stored in a vector database, let's look at how this is used in a typical RAG system. Okay, you've been really patient, so now let's finally get into RAG. Retrieval-Augmented Generation, or RAG for short, combines an LLM with an external data source, normally a vector database, enabling the LLM-driven system to retrieve relevant information in real time to generate more accurate and context-specific responses. This approach avoids having to modify the LLM itself with additional fine-tuning, making your system dynamic, cost-effective, and adaptable to new information. In this RAG-based system, you'll see that our vector database containing the embeddings is integrated into the overall system. So let me step through a flow of a typical user query. First, the user sends a user prompt to an LLM. The user prompt is submitted to an embedding LLM, which generates a query embedding. The query embedding is nothing more than a vector representation of the text in the user prompt. The RAG system, using this query embedding, performs a similarity search on the vector database. Semantically similar documents are returned from the vector database and then paired back up with the original user prompt and sent over to the LLM. The LLM tokenizer converts both the user prompt as well as the semantically similar documents into tokens. The LLM uses both of these to generate a response. The response embedding from the LLM is converted to output tokens, and from there, the output tokens are converted back to text in the user response. With this example, you can see that RAG provides system builders with a powerful design pattern to augment LLMs by integrating relevant, up-to-date, or domain-specific knowledge from external data sources. RAG is essential when you know that your pre-trained LLM has not been trained on any of this proprietary data. By integrating this external data source containing proprietary data, RAG improves the accuracy and reduces hallucinations. In summary, here are the high-level steps in creating a RAG system. Step 1, gather all of your proprietary data. Step 2, create embeddings using this proprietary data. Step 3, store the embeddings in a vector database. Step 4, build your LLM-driven system so that user prompts are submitted to a special embedding LLM which generates a query embedding. Then have your LLM-driven system use the query embedding to query your vector database to get back semantically similar documents. Finally, have your LLM-driven system send the original user query paired up with the semantic summary documents over to the LLM, which will then use all of this to generate a higher quality response. Quick note, I plan to create 2 back-to-back code-centric videos here in the next few weeks. The first video, using Python and LangChain, will show you how to create embeddings for some example proprietary data, and then it will store the embeddings in a Pinecone vector database. The second video, using Python and LangChain, will show you how to create a RAG system using the same Pinecone vector database containing the proprietary data. Keep an eye out for these videos if this sounds interesting to you. So now you should have a good high-level understanding of RAG, along with why embeddings and vector databases are important components in RAG-based systems. You should also understand that RAG helps system builders integrate proprietary or up-to-date data in LLM-driven systems. Let me know in the comments what you think of RAG and if you see any potential for RAG-based use cases in your organization. Okay, thanks for watching. This video, along with all my other videos in this playlist, are listed in the YouTube description. I invite you to watch other videos on my channel. If you like the way I'm sharing this content, please consider subscribing. When you subscribe, this really helps my channel grow. One last thing, we all love technology, and we're all excited about all the innovation with the cloud and machine learning and AI, but don't forget to carve out some time to live in the real world. Go outside, go swimming, go hiking, go climbing, go surfing, but get out and move your body. And if you do, tell me in the comments. I want to hear about it. And with that, have a great day.